Hi, my name is Evan Turnbull, and this is my presentation on Chapter 12 from James Gleick's book, Information, A History, a Theory, a Flood. Chapter 12 in the Information, A History, a Theory, a Flood by James Gleick is called The Sense of Randomness. Much of this chapter is dedicated to discussing the work of Gregory Chaitin, an Argentine-American mathematician who is intrigued with Kurt Gödel's proof that all formal logic systems must be incomplete and that formal mathematics can never be free of self-contradiction. Chaitin was also intrigued by Claude Shannon's work on information theory and the concept of entropy as uncertainty. Chaitin suggested that this concept was related to what mathematicians refer to as randomness in numbers. It is a simple word, random, and everyone knows what it means. Everyone, that is, and no one. A quote from Gleick. He is essentially saying that randomness is something that is subjective. For example, a certain string of numbers could appear to be completely random to one person, but show that same string of numbers to another person and they might be able to see a pattern or devise an algorithm in which the number could be calculated. Gleick quotes John Maynard Keynes in reference to randomness. What is known in advance, determined by a cause, or organized according to plan, cannot be random. Gleick goes on to state that ignorance, too, is subjective. It is a quality of the observer. He says that randomness, if it does indeed exist, should be a quality of the thing itself. He quotes Henri Poincaré saying, "Chance is only the measure of our ignorance. Fortuitous phenomena are by definition those whose laws we do not know." So then, human ignorance cannot be the base of randomness, and Gleick even goes on to state that researchers have established that human intuition is useless in both predicting randomness and in recognizing it. So, by this way of thinking, only if humans are left out of the equation, one could say an event, a choice, a game, or most simply, a number could then be random. Chaitin proposed that random numbers could not be based on the knowledge of the observer and are instead numbers that could not be computed. Computable numbers, according to Chaitin, meant that a number can be expressed in a simpler form by use of a Turing machine. In other words, in order for a certain number to be computable, it must have an algorithm or a set of instructions for arriving at a certain result, that is, smaller than the number itself. Chaitin concluded that most numbers are not computable because there are simply too many positive integers for there to be enough algorithms to describe them. While it may be possible to prove a number is computable, it might not be possible to prove that a number is incomputable. Chaitin also concluded that the size of the algorithm to compute a number indicated its complexity. Gleick explains that the amount of information in a message can be expressed by the algorithm that produces it, and that the size of a message does not always coincide with how much meaningful information the message actually contains. Claude Shannon followed this train of thought when considering redundancy within a message. The three things that make a message compressible are pattern, regularity, and order. Shannon stated that the more regularity in a message, the more predictable it is. The more predictable, the more redundant. The more redundant the message, the less meaningful information it contains. Gleick then goes on to describe Andrei Kolmogorov's algorithmic approach to measuring the complexity of information, focusing on the object, the number or message, itself. Kolmogorov defined complexity as the inverse of simplicity and order, and, just as Shannon concluded, this corresponds to the amount of information contained in the message. The simpler an object is, the less information it contains. The more complexity, the more information. Kolmogorov, like Chaitin, concluded that the complexity of an object is the size of the smallest computer program needed to generate it. Short algorithm equals little complexity, and vice versa. Gleick then explains that, in the real world, messages that are truly interesting, the ones that we care about, lie in the middle of this equation where pattern and randomness interlace. He uses the example of a piece of box music that has several short sections that are repeated and layered over each other. This creates a simple pattern that contains little information. The repetition interlaced with slight variations creates expectations in the listener and then breaks them. Gleick states it is simple the way a Rembrandt drawing is simple. It does a lot with a little. He is so very right when he says in music, perfect understanding is meant to remain elusive, the place where pattern and randomness interlace. Charles Bennett, a colleague of Chaitin, proposed that the value of a message lies in buried redundancy, parts of a message that are predictable only with difficulty, meaning things the receiver of a message can figure out, but they take deeper thinking to discover. When we assess a value of an object's complexity, we find pleasure when it is neither too cryptic nor too basic, but again, somewhere in between. Bennett is then quoted saying, the more subtle something is, the harder it is to discover. Humans enjoy discovering things on their own. And this enjoyment is especially enhanced when we realize that the answer was cleverly hidden right in front of our noses. Like both Chaitin and Shannon, Bennett believed the amount of information in a message is actually not a good measurement of the message meaningfulness. I personally find this way of thinking to be spot on, especially in regards to music. Music that is packed full of many different rhythms and beats may have more information, but it can be less impactful and not sound as good as music that is simpler. I believe that music follows Bennett's buried redundancy and is often the most enjoyable when there are subtle variations on a repeated beat, like Bach, and that it has far more musical meaning than music that is jam-packed with all different kinds of beats and rhythms. Another modern example that is a source for human entertainment that follows this less is more way of thinking is films or movies. Hollywood action movies that try to stuff their running time with as much action, explosions, and special effects as possible have more information contained inside them per se, but like Gleick explained many times throughout Chapter 12, this does not give the film more meaning than any other film. While the increased amount of information often increases the complexity of the film, this also does not mean the film has more value or meaning. Oftentimes, action films have no subtlety and in turn become predictable, requiring no in-depth thinking by the receiver. I think a good example of this is the recently released Transformers film. The running time is a whopping 2 hours and 44 minutes, certainly chock full of information. However, the film's length did not add to its complexity, and the predictability of the film far outweighed its randomness. It is key to remember that truly interesting messages are ones that lie in the place where pattern and randomness interlace. I find that films that take us to places we know, but where events unfold that are surprisingly unpredictable, are the films that are most worth watching. I think a film that does a fantastic job of this is the film Looper. While it can be referred to as an action film, it is so much more than that. It offers a dystopian future that is not too different from films that I have seen before. This is the pattern. However, the film's plot takes many twists and turns that I had no idea coming, such as Bruce Willis actually shooting a child, and the absolutely fantastic ending that I don't want to give away in case you haven't seen it yet. Here are the quiz questions accompanying Chapter 12. First question. What two powerful abstractions did Kolmogorov believe were bound to complexity and determined if an object was simple or complicated? The correct answer for the first question was A, information and randomness. The Kolmogorov complexity of an object comes down to information, which means the size of the shortest algorithm needed to generate the object, and randomness, which refers to the absence of regularity. The second quiz question is this. Which three approaches did Kolmogorov describe could be used to determine how much information is contained in an object, a message, or a set of data? The correct answer to the second question was C, combinatorial, probabilistic, and algorithmic. Kolmogorov refined Shannon's approaches, combinatorial and probabilistic, that focused on a particular message in a set of possible messages, while the third approach avoided starting with an ensemble of possible objects and instead focused on the object itself. Which important figure from Chapter 12 died in the winter of 1978 from fear of poisoning? The correct answer to the third question was D, Kurt Gödel. Kurt Gödel had become increasingly unstable, and he died of self-starvation in the winter of 1978 from fear of poisoning. This was before Gregory Chaitin could ever meet him. Gödel canceled on Chaitin the one time they were supposed to meet. Question 4. What three terms did John Maynard Keynes use to define what randomness is by speaking in opposites? Correct answer to question 4 was B, knowledge, causality, and design. Keynes tackled randomness in terms of opposites, choosing knowledge, causality, and design. He stated what is known in advance, determined by a cause, or organized according to plan, cannot be random. Question 5. What new measure of value did Charles Bennett develop in relation to complexity and capturing the usefulness of a given message, whatever that may be in a given domain? The answer to question 5 is D, logical depth. Charles Bennett's measure of value was logical depth. He stated that there is no logical depth in the parts of a message that are sheer randomness and unpredictability, nor is there logical depth in obvious redundancy. He believed everything we care about lies somewhere in the middle, where pattern and randomness interlace. He called this buried redundancy. That's all, folks.